Sonication is the act of applying sound energy to agitate particles in a sample, for various purposes such as the extraction of multiple compounds from plants, microalgae and seaweeds. The enhancement in the extraction of bioactive compounds achieved using sonication is attributed to cavitation in the solvent, a process that involves nucleation, growth, and collapse of bubbles in a liquid, driven by the passage of the ultrasonic waves. Ultrasonic frequencies greater than 20 kHz are usually used, leading to the process also being known as ultrasonication or ultrasonication. In the laboratory, it is usually applied using an ultrasonic bath or an ultrasonic probe, colloquially known as a sonicator. In a paper-making machine, an ultrasonic foil can distribute cellulose fibers more uniformly and strengthen the paper. Effects. Sonication has numerous effects, both chemical and physical. The chemical effects of ultrasound are concerned with understanding the effect of sonic waves on chemical systems, this is called sonochemistry. The chemical effects of ultrasound do not come from a direct interaction with molecular species. Studies have shown that no direct coupling of the acoustic field with chemical species on a molecular level can account for sonochemistry or sonoluminescence. Instead, in sonochemistry the sound waves migrate through a medium, inducing pressure variations and cavitations that grow and collapse, transforming the sound waves into mechanical energy. Applications. Sonication can be used for the production of nanoparticles, such as nanoemulsions, nanocrystals, liposomes and wax emulsions, as well as for wastewater purification, degassing, extraction of seaweed polysaccharides and plant oil, extraction of anthocyanins and antioxidants, production of biofuels, crude oil desulfurization, cell disruption, polymer and epoxy processing, adhesive thinning, and many other processes. It is applied in pharmaceutical, cosmetic, water, food, ink, paint, coating, wood treatment, metalworking, nanocomposite, pesticide, fuel, wood product and many other industries. Sonication can be used to speed dissolution, by breaking intermolecular interactions. It is especially useful when it is not possible to stir the sample, as with NMR tubes. It may also be used to provide the energy for certain chemical reactions to proceed. Sonication can be used to remove dissolved gases from liquids, degassing by sonicating the liquid while it is under a vacuum. This is an alternative to the freeze pump thaw and sparging methods. In biological applications, sonication may be sufficient to disrupt or deactivate a biological material. For example, sonication is often used to disrupt cell membranes and release cellular contents. This process is called sonoporation. Small unilamellar vesicles (SUVs) can be made by sonication of a dispersion of large multilamellar vesicles (LMVs). Sonication is also used to fragment molecules of DNA, in which the DNA subjected to brief periods of sonication is sheared into smaller fragments. Sonication is commonly used in nanotechnology for evenly dispersing nanoparticles in liquids. Additionally, it is used to break up aggregates of micron-sized colloidal particles. Sonication can also be used to initiate crystallization processes and even control polymorphic crystallizations. It is used to intervene in anti-solvent precipitations crystallization to aid mixing and isolate small crystals. Sonication is the mechanism used in ultrasonic cleaning, loosening particles adhering to surfaces. In addition to laboratory science applications, sonicating baths have applications including cleaning objects such as spectacles and jewelry. Sonication is used in food industry as well. Main applications are for dispersion to save expensive emulgators mayonnaise or to speed up filtration processes vegetable oil etc. Experiments with sonification for artificial aging of liquors and other alcoholic beverages were conducted. Soil samples are often subjected to ultrasound in order to break up soil aggregates. This allows the study of the different constituents of soil aggregates, especially soil organic matter, without subjecting them to harsh chemical treatment. Sonication is also used to extract microfossils from rock. Topic: Equipment. Substantial intensity of ultrasound and high ultrasonic vibration amplitudes are required for many processing applications, such as nanocrystallization, nanoemulsification, deagglomeration, extraction, cell disruption, as well as many others. Commonly, a process is first tested on a laboratory scale to prove feasibility and establish some of the required ultrasonic exposure parameters. After this phase is complete, the process is transferred to a pilot bench scale for flow through pre-production optimization and then to an industrial scale for continuous production. During these scale-up steps, it is essential to make sure that all local exposure conditions ultrasonic amplitude, cavitation intensity, time spent in the active cavitation zone, etc. stay the same. If this condition is met, the quality of the final product remains at the optimized level, while the productivity is increased by a predictable scale-up factor. The productivity increase results from the fact that laboratory, bench and industrial-scale ultrasonic processor systems incorporate progressively larger ultrasonic horns, able to generate progressively larger high-intensity cavitation zones and, therefore, to process more material per unit of time. This is called direct scalability. It is important to point out that increasing the power capacity of the ultrasonic processor alone does not result in direct scalability, since it may be and frequently is accompanied by a reduction in the ultrasonic amplitude and cavitation intensity. During direct scale-up, all processing conditions must be maintained, while the power rating of the equipment is increased in order to enable the operation of a larger ultrasonic horn. Finding the optimum operation condition for this equipment is a challenge for process engineers and needs deep knowledge about side effects of ultrasonic processes. See also: Ultrasonics, Ultrasonic cleaning, Kenneth S. Susslich.